Silence. Om Chan. Good morning, students. In the last class, we discussed about the equivalent condenser, molar condenser, and the factors affecting the equivalent and molar condenser. What are the factors which are affecting the conductance of an electrolyte? We discussed how the equivalent condenser varies with dilution. Also, we discussed how the molar condenser varies with the dilution. And we discussed about the Colas law, which tells us how to calculate the equivalent as well as the molar condenser at infinite dilution. That also we discussed. This is all about the electrolytic cell. Okay, so in the last classes we discussed all things about the electrolytic cell, the electrolytic conductance. Now today we will discuss about the electrochemical cells or the galvanic cells. Okay, electrochemical cell or the galvanic cell. Okay, so today we will have electrochemical cell, or you can say what is the galvanic cell, or what is the galvanic cell. So what is an electrochemical cell or a galvanic cell? An electrochemical cell is a device which converts the chemical energy into electrical energy as a result of oxidation reduction reactions, or you can say redox reactions. So an electrochemical cell or galvanic cell is a device where indirect oxidation and reduction reactions are taking place, and as a result of this indirect oxidation and reduction, there is a decrease of free energy, and this decrease in free energy is converting into electrical energy. So electrochemical is a device which converts the decrease in free energy, that is the chemical energy, into electrical energy. Okay, and here the most important thing is what the indirect oxidation and reduction reaction. Okay, so before that, first of all we will discuss what is oxidation and reduction. Okay, let us see your oxidation, okay, and your reduction. What is oxidation? The loss of electron is oxidation. In the electronic concept, electronic view, the loss of electron is oxidation, and the gain of electron is your reduction. So whenever substance gains electron, we will say that the reduction of substance is said to take place, and whenever substance loses electron, then oxidation of substance is said to take place. Okay. So suppose for example if I take Zn, okay, it will give you Zn 2 plus 2 electron. Zn solid, we convert Zn 2 plus equation plus 2 electron. So here zinc is converting to Zn2 plus by the loss of 2 electrons. So zinc undergoes oxidation. Oxidation. Right? Now here you see zinc with the oxidation state of 0 converting what plus 2. It is an increasing oxidation state of this zinc metal. Okay, so loss of electron, that is what increasing oxidation number is oxidation. Okay, suppose I have this Cu 2 plus, now plus 2 electron, that is C. CO solid, CO2 plus here equals. So when you say this is receiving electron, means what? Undergoes what? Undergoes reduction. Undergoes what? Reduction. Gain of electron, reduction. Now the zinc is losing electron, okay, and CO2 plus is taking electron. We can say this one is, if we compare now these two, this CO2 plus is taking the electron, so because of the zinc is losing the electron. So the electron lost by the zinc is taken up by what? This CO2 plus. So you can say this CO2 plus undergo reduction because of zinc, or you can say zinc is reducing the copper. So, or you can say zinc will be what the reducing agent. What will be reducing agent. Similarly, CO2 plus is taking electrons undergo reduction. Okay, and this is done by the zinc. So zinc is the reducing agent. Similarly, zinc undergo oxidation by losing electron, and this electron is taken by the CO2 plus. So what you can say, the CO2 plus is oxidizing the zinc, because the electrons taken by this CO2 plus is given by what? Zinc. So what you can say, the CO2 plus is oxidizing zinc. So this is what oxidizing agent. What oxidizing agent. So the substance whose oxidation is taking place is the reducing agent. Substance whose reduction takes place is the oxidizing agent. That means one is giving the electron and other is taking the electron. And the process of giving and taking electrons are taking place simultaneously. That means the oxidation and reduction will take place simultaneously. Neither oxidation nor reduction will take place independently, because if one is given the electron, there must be something who can take it. If somebody is undergoing oxidation, means somebody must be there to undergo reduction. That means that will be the reducing agent, and one is the oxidizing agent. So oxidation and reduction are always taking place simultaneously. So they never taking place independently. And when we are doing this reaction separately in different vessels, that is called what? Indirect oxidation reduction. Okay. So these oxidation and reduction are always taking place simultaneously. And if we are doing this in the separate vessels, that is called what? Indirect oxidation and reduction. And this indirect oxidation and reduction is the basis of your electrochemical cell or the galvanic cell. Okay, so let us discuss how the galvanic cell is being constructed, how it is working, and what is its function. Okay. Let us see the galvanic cell. Or the electrochemical cell. The electrochemical cell or the galvanic cell, first of all, consisting of two vessels. Because we will do what? We will do the oxidation and reduction what? Indirectly in the different vessels. Clear? So we have constructions, we have what? Two different vessels, two different electrodes, two different electrolytes, connecting wire, galvanometer, salt bridge. So these are the apparatus which are required for the galvanic cell or the electrochemical cell. Okay. First of all, two different vessels. We have the two vessels where we will take two electrolytic substances and two different electrodes. Okay. So two vessels. So this is one vessel. Another vessel. Okay. Two vessels. Now we will transfer two electrodes will be there. Okay. This vessel will have one electrode. Okay. And the vessel is having what? And the electrode. Okay. Now one vessel containing one electrolyte, zinc sulfate. So here we will take water. Zinc sulfate is called what? Zinc vessel. Okay. Now other contains what will be other electrolytes called what? Silver sulfate. Copper vessel. Okay. Now this each cell consisting of what? Electrode. The vessel where zinc sulfate electrolyte is there, that will contain what? The zinc electrode. What is the zinc electrode? And this is what? The copper electrode. Okay. So we have the two different electrodes. One is zinc or zero copper. Okay. And we have two different electrolytes. One vessel contains what? Zinc sulfate, other contains what? Copper sulfate. And zinc electrode is dipped in the vessel where the zinc sulfate electrolyte solution is there. And copper electrode is dipped in that vessel where copper sulfate solution is present. Okay. Two different vessels, two different electrodes, and two different electrolytes. Now these two electrodes are connected by means of by connecting wire. What will be connecting wire? Okay, and we have a galvanometer here. This galvanometer will show the difference of the flow of electric current on through this way. Okay, connecting wire. And again we have a salt bridge. Salt bridge. Okay. So two vessels contains the electrolytic solutions of two different electrolytes. One vessel contains zinc sulfate, other vessel contains copper sulfate. Solution of sulfate, solution of zinc sulfate. Now each vessel containing one electrode, and that electrode here we have zinc sulfate, so we have the zinc electrode. Here we have copper sulfate, so we have the copper electrode. Okay, and now these two electrodes are connected with the help of what? With the help of your pointing wire, and here we have a galvanometer that will show the difference of current. and we have a short bridge here that connects these two vessels. Okay. Now when this wire is connected to the two electrodes, okay, what happens now? So this is the compressions of this galvanic cell, electrochemical cells. Now you are working. How it was? See, in this electrochemical cell, when we connect this through the wire, here what happens? So at the zinc electrode, zinc undergoes oxidation. Zinc undergoes oxidation to give generative sign, and electrons are being liberated. Okay. And because of the zinc electrode undergo oxidation, it is called the anode. Anode, because the electrons are releasing here, okay, and these electrons are now flowing through this conducting wire, okay. Now because the electrons are releasing here, this electrode is taken as the negative electrode. Okay, so zinc oxidation take place at zinc electrode is taken as the anode, and the charge is negative, and this is in the left side. So here you can say LOAN. That is what? Left oxidation, anode negative. Left oxidation, anode negative. So in the left side of the galvanic cell, we have the oxidation half cell. So in this cell, oxidation is taking place, which is called oxidation half cell. Okay, so left in the galvanic cell we have two half cells. This one is called one half cell. We have two half cells. In the left side we have the oxidation half cell. This is because here oxidation is taking place, and this electrode is either anode and charge negative. So left oxidation, anode negative. This is also called oxidation half cell, and zinc is the anode and the negative electrode. Now when this undergo oxidation, now this electron released are flowing through the wire and comes to this place. Here we have CO2 plus. Now these CO2 plus ions are here. Now this CO2 plus receives electrons in this one CO side. That is saying copper is deposited here. So at the cathode there is and this is called your cathode. Here there is a receiving of electron. So here it undergo reduction. Reduction. This is called what? Reduction half cell. Called what? Reduction half cell. Called what? Reduction half cell. This is called what? Reduction half cell. Reduction taking place here. And here at the cathode there is a demand of electron. There is a demand of electron. That means this is electron deficient. So charge is positive. Called what? Cathode. So in the right side, reduction takes place. Electrode is the cathode, charge is positive. This is called what? Reduction half cell. Now in the whole process, we have seen there is a flow of electron from this zinc electrode to the copper, and from the left to right, or from the oxidation cell to the reduction cell. Okay, and we know electric current is nothing but the flow of electron. So because electrons are flowing from this side to this side, so the conduction current is flowing from this side to this side. And this flow of current is shown by the galvanometer. Clear? Okay, so the current will flow through the external circuit. Okay, and that is shown by the galvanometer. Okay, so in this way, there is a production of electric current as a result of chemical reactions. And this cell which is generating the electric current as a result of chemical reaction is called galvanic cell or the electrochemical cell. Okay, is that clear? So now, and when there is a flow of electrons from this side to this side, from this side to this side, what happens here? Here we have the Cu support, so Cu2 plus support 2 minus. Now Cu2 plus will receive electron and gets what into get converted to Cu. And gradually there is increase of the SO4 to 2 minus ions. There is gradually increase of the negative ions. When there is a gradual increase of negative ions, now when electrons are coming towards the cathode, towards this vessel, the electrons cannot be received at the cathode easily because there is a accumulation of negative ions here. So what will happen? After some time, okay, there will be stopping of the flow of electron. The flow of electron will stop, so that the current flow will stop. That means the cell will not work because the negative charges are accumulated here. Instead of this also happens here the particles also are accumulated here. There are 2%. So when the charges will accumulate, so the flow of electron will stop. That means the electrochemical cell will stop to work. So to avoid this, we have here the salt bridge. We have here the salt bridge, and that salt bridge contains inert electrolytes, KNO3, which are not taking part in the electrochemical reactions. And depending upon the demand of the cell, so if the negative charges are being accumulated in the cell, then the salt bridge is releasing the positive ions to this, so that there will be electrical neutrality will be maintained. Similarly, so here if the particles are being accumulated here, then the salt bridge is releasing the negative charge to maintain the electrical neutrality. So when we have the salt bridge is maintaining the electrical neutrality among the cells, and there is no accumulation of charges on the vessels, so that there will be frequent flow of electrons from one cell to another cell, and accordingly the current will flow from one cell to another cell. And also the salt bridge is connecting the two cells. So salt bridge is a new tube, okay, that contains inert electrolytes which are not taking part in the chemical reactions. Okay, and this salt bridge is connecting the two half cells, and also it maintains the electrical neutrality among the vessels. Okay, so whenever there is accumulation of charges, that is erasing the opposite ions and maintaining the electrical neutrality. Okay, so this is the working of the salt bridge. Okay, so if we don't have the salt bridge, then the cell will start to work, but after a moment it will stop working. There is no flow of current. Okay, so salt bridge is a must in this electrochemical cell. Okay, so this is all about your electrochemical cell or the galvanic cell. Okay, now these cells, this generally we have taken this called zinc support cell. Okay, Now this cell we can represent though in different manners. So, for example, this cell, this is zinc copper cell. Then here the electron is what you here the electron is what you the zinc giving what you Zn2 plus also 2 electrons. Okay, this is what you oxidation. Okay, anode. Then Cu2 plus 2 electron what you Cu solid equation solid is what you reduction cathode here. Okay, so next you can say Zn solid plus Cu2 plus equation will give what? Zn2 plus aqueous plus Cu solid, and here the number of electrons n is what will be number of electrons. So number of electrons what will be 2. This is called what will cell reaction. This is called what will cell reaction. Okay, cell reaction you can write what is happening at the cathode, what is happening at the anode, and what is the net reaction. Okay, so this is the reaction at the cathode, this is the anode. Okay, this is the cathode, and now this is your at anode. Okay, at anode, this is what you at cathode, this is what you the net reaction. Okay, now and the number of electrons required here is 2. This is called your cell reaction. So for each cell there is a cell reaction. Reaction at the cathode, cell at the anode, and the net reaction, and the number of electrons involved also we will calculate. Now each cell can be represented as per the IPAC recommendation. How can we represent a cell? See, for example, this cell, in this cell, so zinc and zinc oxidation type also, so zinc is the anode. So already I told you, we will write value LON. So zinc 2 plus anode. So anode is always written in the left hand side. Okay, in the electrochemical cell. Then what will the salt bridge? Then what will cathode? Cu2 plus C. Okay, so Zn2 plus is what? Anode here in the left hand side. Then what will salt bridge? Then what will cathode? So we can represent the cell like this model. First anode, then a parallel line with salt bridge, then your cathode. Also we can write like this. Simply Zn column Zn2 plus, okay, salt bridge Cu2 plus column C. Okay, this also can represent. Okay, now we can also represent like this. If concentrations are given, right? Suppose you Zn2 plus, suppose 1 molar concentration, salt bridge Cu2 plus 1 molar C. This also clear. Okay. So these are different ways of representing the electrochemical cells called what? Cell notations. Okay. How can we represent? First we write a node, then salt bridge, then the cathode. Anode always in the left hand side, then salt bridge, then cathode. Zn plus Zn2 plus anode, salt bridge, Cu2 plus cathode. Organize you Zn column Zn2 plus salt bridge, Cu2 plus column C. If concentrations are given, Zn2 plus 1 molar concentration, salt bridge, then ion concentration, then your column. This is the solid. These concentrations are not required. Okay, 1. Just add the concentration of the ion. Okay, so in this way we can represent a particular electrochemical cell. Okay, this is called what will be cell notations. Okay, so if the conditions are standard, If the conditions are strong, suppose one more concentration is there, and also we have your room temperature 25 centigrade, then the conditions are called your standard conditions. Okay, this is all about galvanic cell or electrochemical cell. Now next we will discuss what is the electrode potential. Okay, electrode potential. Okay, so now electrode potential. Electrode potential. What is electrode potential? It is the tendency of an electrode to lose or gain electron. We have seen in electrochemical cell, in the oxidation half cell, the electrode is losing the electron. Oxidation takes place there. In the reduction half cell, the electrode is receiving electron. Reduction takes place there. So, an electron can lose electron or can gain electron. Accordingly, it may undergo oxidation or reduction. Okay. So, the tendency of the electrode to lose electron or to gain electron is called what? It's a electrode potential. The tendency to lose electron is called oxidation potential, and the tendency to gain electron is called the reduction potential. Okay, so whenever an electrode is losing electron, it is undergoing oxidation, and its tendency to lose that electron is known as its oxidation potential. And whenever an electron is gaining electron, it undergoes reduction, and the tendency of that electrode to receive electron is called as reduction potential. So every electrode is having their own reduction potential and their own oxidation potential. So how to calculate the electrode potential of a particular electrode? We know neither oxidation nor reduction are taking place independently. Always they are taking place simultaneously. So if you want to measure the potential of a particular electrode, we have to couple it with another one. So whatever potential we will notice on the galvanometer, that will be the difference in potential of the two. So it is not possible to calculate the absolute value of the electrode potential of a particular electrode. Okay, so tendency to lose electron is what? Oxidation potential, OP. Tendency to gain electron, reduction, RP. Okay, but to measure the either oxidation potential or reduction potential of a particular electrode, that is single electrode, is not possible. We cannot calculate the absolute value of the potential, so we have to couple it with the another one, and when we couple it with the another one, so that potential becomes the difference of the two. So for this purpose, what we are doing, we are doing what to calculate the single electrode potential. So because calculation of the single electrode potential is not possible, so what we are doing, for this purpose we are taking a standard hydrogen electrode SHE, or we are taking a normal hydrogen electrode NHE. So the potential is what? 0.0. तो standard hydrogen electrode or normal hydrogen electrode is taken as standard, and whatever electrode will take to calculate its potential will couple that electrode with this SHE or NHE, so that the potential difference which will record is only meant for the electrode which we have taken, because its value is 0. The potential of the standard hydrogen or the normal hydrogen is 0 volt. Okay, and what is called your standard electrode potential? If we calculate the potential at standard condition, that is what 1 molar concentration and what at 298 Kelvin. If the electrode is suspended in 1 molar concentration of electrolyte at 298 Kelvin, that is called what? Standard electrode potential E0. Okay, see, standard electrode potential E0 is what? Potential at 1 molar concentration of electrolyte at 298 Kelvin is called what? Standard electrode potential. So when you calculate this standard electrode potential by coupling it with the standard hydrogen electrode or the normal hydrogen electrode, so then the potentials will be referred to the potential of the electrode which we are going to determine. And here, depending upon the other electrode which we are taking, the NHE is behaving as a cathode or as anode. Okay, that means if the electrode which we are taking is acting as anode, that means oxidation taking place there, then the NHE will act as a cathode and reduction will take place here. If the electrode whose electrode potential we are going to determine is acting as a cathode, that means reduction taking place there, then the NHE will act as anode and oxidation will take place here. So depending upon the nature of the other electrode present, the NHE can behave both as a cathode or as an anode. That means the normal hydrogen electrodes may undergo oxidation or may undergo reduction. Okay. Cell potential or EMF of the cell, electromotive force of the cell potential or EMF of the cell. So we know in a cell, in an electrochemical cell, we have two half cells. One is the oxidation half cell and other is the reduction half cell. So when we have the electrochemical cell, the cell potential or the electromotive force is the difference in potential of the two electrode potential of the two half cells. Okay. So because the electrochemical cell is consisting of the two half cells, so the total cell potential is the sum of the potential of the two half cells. Okay. So what we can say, the cell potential or EMF is equal to the oxidation potential OP of oxidation half cell plus reduction potential Rp of reduction half cell. Okay, so cell potential or EM is what? Oxidation potential of the oxidation half cell and reduction potential of the reduction half cell. Okay, and we know oxygen occurs at what? At anode, reduction at what? Cathode. Okay, so inert cell is equal to, okay, inert anode OP plus inert cathode RP, because we know reduction takes place at a cathode, oxidation takes place at anode. Okay, or you can say inert cell is equal to inert right OP plus inert left, inert right, inert left, anode left OP plus inert right RP. Okay, so oxidation potential of the left electrode, that is the oxidation at left, plus reduction potential of the right electrode, that is your cathode. Now from this you can say inert cell is equal to, we have inert anode OP. Okay, inert anode OP okay minus inert cathode OP. See, reduction potential of cathode is equal to what? Minus OP of cathode. Okay, so because if oxidation potential of a particular electrode is x volt, then its reduction potential will be what? Minus x volt. Just reverse. So E not cathode equal to what? Minus inert cathode OP. Inert cathode RP equal to minus inert cathode OP. So we can say inert cell equal to inert anode minus inert cathode in terms of what? OP. In terms of oxidation potential, inert anode minus inert cathode. Now, if I will go for reduction potential, right? Inert cell is equal to, see, inert anode OP again value minus inert anode RP, okay, plus inert cathode RP. That is what inert cell equal to inert cathode minus inert anode in terms of what? RP. Okay, or you can say here inert cell is equal to inert cathode means what? Right minus inert left. What is the standard one? Inert cathode minus inert anode in terms of RP. always we can calculate in terms of reduction potential, that is what inert cathode minus inert anode. Okay, or you can say inert right minus left. Okay, so this is in terms of what RP, or in terms of OP, inert cell is equal to what? Means oxidation potential inert anode minus inert cathode. You can say inert cell is equal to left minus right. Okay, so in terms of RP, cathode minus anode, in terms of OP, anode minus cathode. So this is the way how to calculate the cell potential, okay, of a particular electrochemical cell. So if simply OP of anode and OP of anode and RP of cathode given, you just add the two values and get the cell potential. And if we have only RP, the cell potential, you just go for what? Cathode minus anode. And if OP given, go for what? Anode minus cathode. Or if it is given, you convert it to your ORP, then you calculate. Any one which choice. Okay. So generally we calculate in terms of what? RP, cathode minus anode. Now let us have an example of basing on this calculation of potentials. Okay. See, suppose here are given calculate the cell potential of the cell as per the data. As per the data given. Number 1. Zn2 plus Cu2 plus Cu. Okay. Given here the given E naught Zn2 plus by Zn is equal to minus 0.76 volt. The E naught Cu2 plus by Cu is equal to 0.34 volt. Okay, is the given data of the potential. Okay, now see, this is the cell, this is what your anode, this is what your cathode, this is solvent. So left anode oxidation, cathode what? Reduction, given the cell. Now see, the E naught cell is equal to E naught cathode minus E naught anode in terms of what? RP. In terms of reduction potential, E naught cell equal to what? The cathode minus E naught anode. So who is the cathode here? Who is the cathode here? Cu2 plus Cu. How much is the value? 0.34. So put here is equal to 0.34 minus inert anode. Who is the anode here? This is the anode Zn2 plus. Okay. What is the RP value? 0.76 minus suppose 0.76 equal what? 1.10 volt. Okay. So the cell potential, the standard cell potential inert cell equal to what? The 1.10 volt here. The data given here in terms of RP. So how can you calculate the cathode minus anode? Okay, equal to this one. Suppose for the same cell, number 2, Zn2 plus CO2 plus CO given here E naught Zn2 plus is equal to 0.76 volt and E naught CO2 plus equal to 0.34 minus 0.34 volt given here. You see. Same thing, this is your anode, this is your anode, this is your cathode. Like given here Zn2 plus that means 0.76 volt, that means OP given, oxidation potential given here. This is what CO2 plus, again here OP given here. So we know E naught cell is equal to E naught anode minus E naught cathode in terms of what? OP. In terms of OP, inner cell equal to inner anode minus cathode. So who is anode here? Zn2 plus. How much given here? 0.16 minus cathode. Who is cathode here? This one cathode. How much given here? Minus 0.34 equal what? 100. Same way. In terms of Rp, C minus A. In terms of OP, A minus A. Value same. Okay. Number 3. Suppose we have Zn2 plus solve with CO2 plus CO. Given here E naught Zn2 plus is equal to 0.76 volt and E naught CO2 plus CO is equal to 0.34 volt. Here you see, is the cell, is the anode, is the cathode, and here this is the anode, and given here what? Zn2 plus is OP given here. OP given here. OP 40 anode given here. CO2 plus CO times value. Rp given here. 40 cathode. So Rp for cathode, OP for anode. Therefore, E naught cell equal to what? E naught cathode plus E naught anode. Cathode Rp, anode OP. Okay. So cathode Rp how much? 0.34 plus anode OP how much? 0.76. Answer 1.1. So if cathode Rp given, anode OP given, just do air. If only Rp given, see cathode minus anode, only OP given, anode minus cathode. So this is about how to calculate the cell potential of a particular electrochemical cell. Okay. So in the next class, we discuss about the electrochemical residue and its applications. Okay.